Hello?
Good morning.
Morning. Hello, Shyam?
Yeah, hi.
Hi, how are you?
Hello.
I'm fine. This is my first time joining orals meetings.
Okay.
Yeah, I've already introduced myself on Slack, and I think I've sent a direct message towards your direction. I'm interested in the sales GSOC.
Okay.
And yeah, I'm currently drafting up the proposal. I'm 70% there. I joined this meeting, and I think I have a couple questions regarding the project and the scope of it and all. I was hoping I could get some answers here.
Okay. All right.
Yeah.
What were your questions?
Okay. So I think the first one is about the scope of the project. I wanted to ask if we are trying to move away from 2-3 agents to something like more somewhat of a multi-agent system which has a lot of agents, a swarm type thing, where we have multiple contributors coming and then looking at the say the repository that we're modeling or the open source community that we're modeling, and then we have multiple maintainers voting on each contributor's tasks and then their methods of approaching that problem, and then we also have somewhat of a state management system where we're keeping track of the open source system that we're modeling over multiple different time steps. I was thinking to do that, we could have a database sort of thing so that we don't have to start our system again every single time we run the simulation, so that we can have the growth that happens in the system stored over multiple time steps. And then when we come back and run the simulation again, we could just retrieve our previous state from the database and then keep building on top of that.
Yeah. So yeah, I don't know. I guess you mean like over multiple sessions?
Yes.
Yeah. So yeah, I don't think we have that capability built in. I'm not really sure how it's, but yeah, we have well, last year we did, of course, the large language models and agent-based models hybrid. But we also did some work on, or we've been doing work over the past several years on multi-agent reinforcement learning.
Yeah.
And so that can be, that's sort of the multi-agent approach. Now, it'd be interesting to integrate swarm type models or swarm intelligence type models into that, or to treat it more as kind of like a collective behavior type model. I'm not sure what the literature looks like in that area, but it'd be interesting to see. But yeah, there is a whole bunch. We've been kind of working in a certain direction on the multi-agent reinforcement learning. And so there's a repository there to build on. So yeah, I mean that would be another thing to do. I think it would be interesting.
Okay.
There was also some work that was done last year, and I don't think it got very far, on integrating multi-agent reinforcement learning with like the large language models. So large language models would generate like a project and some tasks, and then the multi-agent system would interact with that and use those tasks. So I don't know how far that we got on that. I don't think very far though.
Yeah. From what I've seen in the code base, it looks pretty. There's only a couple agents, and they're doing pretty basic tasks. So there's a calculator model which the contributor and the maintainer just are trying to build over. So I was thinking, in my proposal for what I'm going to submit this year, I was thinking maybe I could build on what's already here, and then try to make a swarm type of thing where I have more LLM based agents working together, and then we could have a majority voting based type of swarm model. There are a lot of swarm models that I've looked at. There is this one specific Python library called Swarms, through AI and things like that. These are agent orchestration tools. I was thinking maybe I could try to build my proposal around that direction.
That sounds good.
Okay.
Yeah. Okay. Yeah, definitely. Yeah, I don't. Yeah, I guess if you had a package in mind, that would be useful. Because I don't know how, like, when you get to the memory management aspect of it, how many agents you can actually put in the environment. So If there's a package
Yeah,
though, it'll be able to handle those sorts of computations.
yeah, exactly. So, are there any other ideas that you specifically want me to focus on in my proposal?
No, I think that would be good. If you could hit on those points, and like I think the key is to say I'd integrate it into the existing code base.
Right, right,
Yeah.
right. Okay, sounds good. Thank you so much.
You're welcome. You're welcome.
Thank
So
you.
yeah. So yeah. In terms of meetings this week, we had our DevoWare meeting last Monday. And we still haven't had our cybernetics or cognition futures meeting. So welcome, Morgan.
Good. I keep having meetings before this meeting,
Yeah.
which is already an early. So I'm going to. I still haven't had breakfast.
Oh yeah.
Anyway, good. Lot happening this week, but mostly neurotech meetings and recruitment and just discussing future projects. So good stuff, but a lot of generating, like a lot of seeing if people are if we can work on educational material, not yeah. So
like educational material for
around supporting some of Neurotechnic's projects and in particular software projects.
Oh, okay.
So I still so our most GitHub starred project is the mother of all BCI benchmarks, and it's still a great it's like, besides its unique application area, it's a great sorry, something's ringing on me. Okay. It's a great intro project for students to get familiar with scikit-learn, for instance, and I like that in terms of a lot of neuroscience and cog sci students are always asking about how to break into neurotech, and it's like there's not a lot of neurotech jobs.
Yeah.
And so it's like, what's the best thing we can do to prepare them for the larger job market? But it was really nice. I met with the students organizing the California Neurotechnology Conference, which is a great student-run conference of the neurotech chapters from the various UC schools and other California institutions. So that was it's great to see, and they've got some great speakers. So that's another reason to work on our kind of marketing and educational materials. Like, I'd love to go down and use it as an opportunity to get more students involved in the project. Because it's also one of those projects where it's just like what's the I forget who said this, or knowledge is the only thing that grows when shared.
Oh yeah.
Anyway, but that this is a wonderful project where it's like it actually gets better by having more people, and it gets better by people adding more data and adding more implementations.
Right.
And yeah, so I'm also pushing it as a good project to have the different student chapters coordinate together. Like it's a project that they can all work on and benefit from, and that kind of coordination like could actually push it into to a level that we could get a paper,
Yeah.
because it's already got anyway, like the French team that develop it, it's a kind of it's a cool geometric methods for machine learning classification. They've already got a good archive paper, around its most recent, it's like forget the title, but it's like the largest EEG, benchmark. And yeah, it's got projects that fit in a kind of like a number of different kind of like experience, or like there are projects which are coding, and then there are projects that are kind of like data munging,
Right.
and the like seeking, almost like literature review, like finding data sets, getting them into that form, and then updating. Yeah, so lots of different expertise levels can participate. And I'm trying to think of any organoid news. But anyway, we can update on that later.
All right. Sounds good. Thank you for that update.
Yeah.
All right. So the first thing I wanted to talk about today was we, of course, have our Slack. So if you're not in the Slack, please, explore the Slack. I know that like people are coming in from, outside, and so they probably aren't familiar with it. We have a general channel, which is where you kind of end up when you join. And, I think Shyam and Vidhi have introduced themselves. So that's key. And then we have our sub-channels. So we have all sorts of channels. We have data science, bioevolution, a GSOC channel that's useful, virtual reality channel, and some other channels. And then we also have some Discord servers that serve as kind of a backup to those channels that we don't use as often, but are still sort of available for people to go to. Those Discord channels and the Slack team are all linked off of the main lab website, which is orthogonal-research.weebly.com. So go there and you can find the links. This is one of the things from the Slack here. I think this is something that Morgan posted. This is an article from Google Research on differentiable logic cellular automata. So in the DevoWorm group, we've been exploring the neural cellular automata. We did some work on this a couple years ago, actually. And then beyond that, we haven't really done a lot with it. But people have been picking this up in the last few years and trying to build pattern generators out of them. So it's very interesting work. And so, if you go back to the original cellular automata, those are very old computational systems. They go back to Elise von Neumann. And the idea of a cellular automata, of course, is you have a central cell with neighboring cells. And the neighboring cells, depending on their state, govern the the sort of the focal cell state. So let me draw this out on a whiteboard. So in a cellular automata, you might have a neighborhood of cells, and usually, there's the von Neumann neighborhood and there's the Moore neighborhood. So they can look, in different ways. So I'm just going to draw a unit of analysis here. So in this kind of a neighborhood configuration, you have the focal cell, which is here. And in this kind of configuration, you have the focal cell, which is here. And then you have neighboring cells. The neighboring cells are always one cell away from the focal cell. And so you can think of this in terms of XY coordinates. This is -1, -1, so they all have a position. This is 0, -1. This is 1, 0. Yeah, this is actually not -1. This is 1, -1. This is -1, -1. This is this -1, 0. I'm trying to remember my coordinates here. It's something like that. Anyways, if you label this grid, you end up with these neighbors in specific positions relative to the focal cell. And in this case, you have the same sort of coordinate system. Now, the interesting thing about these focal cells is they're affected by the neighboring cell states. So, for example, if we have this type of neighborhood, and our focal cell is here, if a majority of these cells are shaded, let's say the initial state is that they're all sort of off, and then when this squiggly line here, which is kind of shading it in, is going to be where the cell is turned on. These cells are all turned on, and it's a majority of the neighbors that are turned on. And so we might have a rule that says if a majority of the neighbors are turned on, then on. Which means that if a majority of the neighbors are on, then the focal cell is on. So then the next state, which is t+1, so this is t and then this is t+1, the focal state will be on. Okay, so that means that we've turned on our focal cell. So, these are all on. And the same holds true for this type of neighborhood as well, where it's, a majority rule where the neighbors are, if they're on, then the focal cell will be on. And, you can use that majority rule the same way to go turn it off as well. So if the majority cell is on, then the focal cell will be off. So this is, one type of rule. We can have other rules. We can have rules where, we basically, if one cell is activated, then the focal cell is activated. We can have rules where all the cells have to be activated for the focal cell to be activated. It depends on our sensitivity and all that. Now, you have to remember that these neighborhoods are all kind of nested together in the sense that they're operating in parallel. So if we take the square neighborhood like this, and we imagine that we have this implemented in parallel, that means that this is the focal cell for this neighborhood. And then this neighborhood then extends out. So this is neighborhood A, this is neighborhood B. This neighborhood B will have a focal cell here. So this is focal cell A, focal cell B. And you can see you can create neighborhoods all the way across a larger matrix of cells. So this might be, kind of ran out of space here, but you get my point. neighborhood C, where you have a focal cell, which is here. And this keeps going all the way across the grid. And so you have these focal cells affected by the neighboring cells, and you have this these computations that occur in parallel. So you can have effects where things either form patterns, stable patterns, transient patterns. Sometimes you have cascades that cascade across the larger grid. Sometimes, in what they call the game of life, you have things like gliders and other types of structures that move across the grid as cells are activated, and those rules are activated and they turn on. Sometimes you have things that just kind of jam up, where everything is activated and then it's saturated, and you just end up going from where everything is off to where everything is on. Sometimes you get coherent pattern formation, though, and that's what we're going to be talking about in the Differentiable Logic Cellular Automata paper. So this is, the subtitle of this is From Game of Life to Pattern Generation with Learned Recurrent Circuits. So the basic idea of a cellular automata, of course, is based on these neighborhoods and how you can implement these rules to activate these cells collectively. In a neurocellular automata, we use different types of tools. We use different types of machine learning techniques, neural networks, and things like that. And so that's where they're kind of drawing from here. This is why there's been a rebirth of cellular automata. People have used cellular automata to look at complexity, to look at the implementation of different types of pattern formation. They've used different types of rule sets. So, for example, if you have different types of rule sets, you can generate different patterns. So, Wolfram has described, you'll have something like, he uses triangles in his work. And you get these triangular neighborhoods or these triangular grids where they get activated across kind of like this. And, there are different patterns. So you get things that look like seashells. You get things that have like stable periodic patterns, and those have different numbers attached to them. So, there's like rule 120, rule 60, rule 30, and they just are implemented in different ways using different rules. And so, those kind of models are great for pattern formation, but there isn't a lot of control there, and it's just kind of a curiosity. So this is why we're interested in implementing more machine learning techniques here. So let's go through the paper here and see what they have to say. This is a paper, kind of a big money approach to this. This is like the, a Google research team called the Paradigms of Intelligence team. So that's where they're coming from. Randazzo is named, they published a lot of things on, I think, some of the other neurocellular automata work that we've talked about in Vivo. Okay, so imagine trying to reverse engineer the complex, often unexpected patterns and behaviors that emerge from simple rules. So this statement is basically that one of the things about pattern formation and what we might call emergent phenomena, which is where you get these patterns that come from these interactions, is that a lot of times they're not reverse engineerable. In other words, you can forward engineer them by generating a cellular automata and running it for a number of generations and getting these patterns. And you can, same thing with swarm intelligence, where you run a bunch of agents in a simulation and you can get them to form patterns. And that's, we talked about emergence, weak emergence, strong emergence. But the thing about emergence is that it's usually not reverse engineerable. In other words, there's no inverse way to evaluate this. So this is kind of what they're getting at here, where, you try to reverse engineer these complex patterns. And in fact, in a lot of cases, you can't do it, because what happens in an emergent system is that there are many different ways to get to that pattern. So it's not so much that you can isolate it to specific interactions. It's that those patterns emerge from many different possible configurations of the system. So if you think about an ant colony where you have ants crawling along and forming pathways that they can traverse, and then you look at say like an ant colony optimization algorithm, which we talked about last week, and you see this pattern form. They can form that pattern by using many different routes and route following strategies. It isn't just, you can't isolate any single pattern to any set of specific interactions. So that's where we are with this. And so they say this challenge has inspired researchers and enthusiasts to work with cellular automata for decades. So, people have been working on this kind of approach that goes bottom up. So in a cellular automata, you start with these neighborhoods, you start with these interactions, these focal cells are changing their state, these focal cells are also organized in parallel, and you get these emergent patterns that come from the bottom, which are these neighborhoods, up to the entire grid. So you end up with these kind of triangles with periodic patterns. And that's what they mean by bottom up. We choose local rules, then investigate the resulting emergent patterns. But what if we could create systems that, given some complex desired pattern, can, in a fully differentiable fashion, learn the local rules that generate it, while preserving the inherent discrete nature of cellular automata? So again, these are discrete models. We have these cells. It's a discrete model in time as well. So these neighborhoods change their state with time. So we go from t to t1 to t+2 to t+3. And in each state, these focal cells change. And so when you get like something like a glider that moves across this grid, that's the product of time evolution. It's also the product of discrete state evolution as well. So that's what they're going to talk about here. So their interest is in building these learned circuits. And then what they want to do here from this learned circuit is they want to build this G, Google G. They could have built anything, but they decided on the corporate logo. So, but anyways, in any case, you see how this pattern is forming from these interactions. But what's interesting is that you can do this through implementing rules and just watching the simulation go, or you can build these circuits that you can then go back and trace the evolution of this. So you know what part of the circuit has been activated when, and you can trace back the formation of that pattern. So that's what they mean by differentiable. That allows us to have a differentiable system as opposed to something that's merely emergent. Prior work has explored learning transition rules using non-differentiable techniques, demonstrating the feasibility of evolving local rules for specific computation. And this citation is from Physica D in 1994, Melanie Mitchell, Jim Crutchfield, and Hraber, Evolving Cellular Automata to Perform Computations. So this is work that goes way back. This is this original type of work that people were doing with emergent patterns in cellular automata. Likewise, prior exploration of making one-dimensional cellular automata differentiable exist. So there's this paper from 2017 by Martin on the archive called Differentiable Cellular Automata. So people have been exploring this sort of approach for a while. And this, again, is an approach to making emergent phenomena understandable at the level of like specific interactions. We propose a novel, fully end-to-end differentiable approach, combining two interesting concepts in the world of artificial intelligence. So the first is neural cellular automata, which I mentioned. This is a thing we've been looking at in DevaWorm. We worked on it for a little bit. This is an article from Mike Levin, Randazzo, and colleagues. This is in Distill, which is the machine learning journal. And this is, of course, the paper Growing Neural Cellular Automata. I think we've covered this in DevoWorm meetings in the past, this is where, they're basically building cellular automata with a neural network architecture, and then they're trying to grow these they're trying to implement pattern formation, growing phenotypes, things like that. It's very interesting work. And actually in the Google Summer of Code DevoWorm project this year, we're doing things with these neural developmental programs, which have their roots in neurocellular automata. The second concept, neurocellular automata, is the first concept. The second concept are differentiable logic gate networks. And so these cited works here are this paper, Deep Differentiable Logic Gate Networks. That's a NeurIPS paper from 2022. And then Convolutional Differentiable Logic Gate Networks. That's also a NeurIPS paper from 2024. So this is an emerging idea as well, where you have these logic gate networks that describe sort of these interactions on this grid. So every one of these rules and in these neighborhoods is basically a logic gate. You have to satisfy the condition, and then the logic gate is activated. Otherwise, it's not. That corresponds to whether this this focal cell was activated or not. So that's the idea. And then for each neighborhood at each point in time, there's a circuit that's turned on or off. And you can build differentiable rules from that, or you can use it as a differentiable system. NCA exhibits the ability to learn arbitrary patterns and behaviors. However, they do not inherently operate within a discrete state space. So NCA models, these neurocellular automata models, don't operate in a discrete state space. So it's hard for people to interpret the output. So, if you think that regular cellular automata are hard to interpret, or their interpretability is low, NCAs, I guess, are even worse because they don't necessarily operate within the space that a traditional CA operates. So their interpretability is made more challenging and leaves them stuck in a regime where current hardware must perform costly matrix multiplications to gradually update their continuous internal states. Differentiable logic gate networks, meanwhile, have been used to discover combinatorial logic circuits, blending discrete states with differentiable training signals. But they haven't yet been shown to work in recurrent settings. NCA, as it were, are recurrent in both space and time. Sounds intriguing, right? So they're talking about using these two different methods, and then they're talking about the integration of these two methods, differentiable logic gates and neurocellular automata, as a potential step towards programmable matter. And they use the word computronium, which is this paper from 1991. It's kind of a visionary paper from Science, and it's speculating in precious computronium. So this is like kind of an idea of having this programmable matter as something that we can at least understand computationally. Mike Levin does a lot of stuff with programmable matter as well, and there are other people who do this. A theoretical physical substance capable of performing arbitrary computation. Toffoli and Margolis pioneered this dream with CAM8, a cellular automata-based computing architecture. So this is Toffoli of Toffoli Gate fame, and then Margolis, who published this paper on CAM8, which is a cellular automata-based computer architecture. This is from 1995, so this is a long time ago. This was where they were trying to figure out how to build a computer with cellular automata, kind of going back to von Neumann's original vision. Not the von Neumann architecture, but von Neumann did other work on self-reproducing machines that kind of is in that area. And then programmable matter, concepts and realization in Physica D from 1991. So in theory, these kind of models are capable of immense, horizontally scalable computation. However, they face a fundamental challenge, and they're talking about Toffoli and Margolis, actually crafting the local rules needed to achieve the desired macroscopic computation. With a motto at all noting that other researchers still worry about the difficulty of finding local rules that corresponding to real natural systems. So this is another thing about cellular automata, is that they look kind of lifelike. And in fact, that's kind of one of the arguments that a lot of people make, that the patterns that they form are like things like seashells and other types of pattern formation. And they kind of mimic biological processes in that they form patterns that look biological, look lifelike. But there is no evidence that life actually produces things in this way. This is a purely computational model that produces lifelike patterns. And so it's hard to find local rules for this, right? I mean, you can find the local rules for the computational side, but finding the local rules, say, in biology, and then saying, oh, this is what the model is doing, above and beyond sort of satisfying the conditions of the logic gate, that's sort of an elusive point, and that's what they're making here. So what if we could directly learn these local rules and create models that combine binary logic, the flexibility of neural networks, and the local processing of cellular automata? We believe our prototypes offer a glimpse into the future of computing, which they define as learnable, local, and discrete. So again, local, having these neighborhoods, discrete being these discrete states, and then learnable, which brings in the neural network aspect. This article will walk you through implementing cellular automata using differentiable logic gates and demonstrating some key results. So they had a couple of fundamental questions. Can differentiable logic CA learn at all? And so they actually use Conway's game of life, which is a nice cellular automata model where, they have the cellular automata that runs, and they're able to produce different types of patterns, not only static patterns, but things like gliders that move across the grid and other types of patterns. And this is something where, I guess they're using Conway's game of life to see if those things can be learned. This is kind of an interesting benchmark for that. The second question is, can recurrent in space and recurrent in time circuits? So these rules and these grids are managed by sort of a recurrent process. And so there's this spatial and temporal aspect that evolves over time. It interacts over space. And you have recurrence in space, recurrence in time. And so can that sort of a system learn complex patterns similar to those generated by traditional neural cellular automata? So the neural cellular automata are really interesting, produce good results, but they're not discrete, and they don't allow for this differentiable aspect. This is what they're getting at. This is what they want to do, and they want to be able to trace back to specific sort of forward rules and outcomes. So while both differentiable logic gate networks and neural cellular automata, or NCAs, have demonstrated trainability, effectively training circuits that exhibit both temporal and spatial recurrence of NCA within the framework of differentiable logic remains unexplored. So they do these experiments. They talk about 2D grid of intelligent cells, which is how they describe the cellular automata. They use 3 channels of color. They have an alpha channel, which is where if the alpha value is greater than 0.1, the cell is considered alive, as in Conway's game of life. The hidden channels, which are n-4 channels, allow the cells to communicate more complex information about their environment. So the examples I gave you here were sort of this binary on or off. Now you can change those rules to say something is activated to a certain degree. It can be up to a threshold. It can be maybe just kind of just alive at a value of 0.1, and then vital, or some sort of vitality at like 0.7. You can have different states of being alive. So they're kind of getting at here. And then they have this 2-stage update mechanism the perception stage and the update stage. So this basically this focal cell is a cell that senses the world around it, which are these neighboring cells, and so in their case they use Sobel filters, which are these tools that allow you to approximate spatial gradients numerically. So basically, the Sobel filter, when implemented, changes across its surroundings. The filters are applied channel-wise, and the result is termed a perception vector, which combines the cell's current state with the information it gathers about its environment. So this is kind of like in biology where we use chemical gradients, or we see chemical gradients being perceived by biological cells to align themselves with their surroundings. And this is something that we see in chemical morphogenesis. So the type of Turing morphogenesis that we're familiar with, that's basically the idea, is that you have these gradients, these chemical gradients, and pattern formation follows these gradients and they're sort of their intersection. So then there's the update stage where they put a neural network in the mix where each cell uses its perception vector, which was described up here, as an input to the neural network, which performs identical operations on every cell in the grid. Using around 8,000 parameters, the neural network determines how each cell should change based on the information it has gathered. It's here that the system evolves, with the cells adapting and responding to environmental changes. So this is a figure that shows the NCA from, they're trying to do is evolve this, I think this lizard phenotype, and they're showing how they're using Sobel filters and this perception vector, and then plugging it into a neural network to produce this update. And so this is actually from a growing NCA. So they use a similar process in the growing NCA paper. This is this paper from the Distill journal. And so, what they want to do is they like all this, they just want to reverse engineer. So so they use gradient descent to sort of find these specific steps. So this is a good paper. I like their approach and what they're doing here. Got some things in the chat here. So Vidhi, thank you for posting some things here. This is a post on unveiling differentiable logic cellular automata, new frontier in neural computing. Another blog that I found on the same topic has a good pictorial explanation. So yeah, and then didn't realize, but the blog and paper have the same diagram. Yeah, so this is kind of talking about this work. So a blog post, yeah. And I think this is actually, this figure is from this NCA paper. So this is back from 2021 in Distill. But that's what they're trying to do. They're trying to build this sort of pipeline where they have the Sobel filter, which is sort of determining or detecting spatial gradients. They build this perception vector for each focal cell. They're building this neural network, and then they're updating their model. So all very good stuff. Any other questions? I see Morgan said nice. If Morgan had anything to say about it.
No, I hadn't had a chance to actually work with it or play with it. But yeah, it does take me back to that. What year was that? The first NCA?
Oh, I think 2020. Well, I don't know when the first paper. I know some of the work was in 2020, 2021, but I think it goes back a little further than that, though. Yeah. I mean, I don't know. Yeah.
Yeah, and it's scary to me that was almost 5 years ago.
Yeah. Well. Yeah.
It seems like it was. Yeah.
I think there's some interest. Oh, go ahead.
No, we had somebody come by the biolab, asking about these kind of computational like how do biological simulations work, or
Yeah.
and um, who's got a blog post, or somebody just wrote an essay on the it's a takeoff on the old essay, but it's like the the unreasonable ineffectiveness of mathematics and biology, or something like that.
Yeah.
Like it's like the opposite of was it von Neumann? Who did the first?
Wigner. Eugene
Wigner. Yeah. Thank you. Anyway, so it's just like talking about the difficulty of, or the intractability, or why mathematical biology is so hard.
Yeah.
And so was trying to talk about the models of in developmental biology, and who's doing such things, and how kind of like what features from them do you want to try and extract, without creating a kind of finite element physics model, when there's like yeah. So I thought it was really interesting to see these new very wide images, microscopy images of embryos, and to really capture, like people who are working to capture all the flow.
Oh yeah.
And then when you think about like trying to model that flow, and trying to model it, trying to model it with like what which of those features do you want to capture? So I mean, there's kind of like the how much is cell adhesion changing, how much of the genetic control is important. Again, always, and there's always being good to go over the fact that no cell is in charge of this.
Yeah.
Right. So to some degree, it's it's driven by this cell adjacency, and anyway, so these mathematical abstractions are still still really relevant for these even though they're obviously abstractions, but valuable.
Yeah, I think that's the modeling flow is interesting. People, I think there's a paper maybe in 2020 where they used Lagrangian coherent structures to look. This is a model where you use a Lagrangian to track like flows in liquids. So if you have like a dye that you have dispersed in a liquid, and the liquid is turbulent in some way, you can track those flows using this tool where basically you look at like it's not a discrete model in the conventional sense. It's just you take two particles and you track their distance or their difference. So you have this differentiable model, but you also have this description of these flows because you get these structures that sort of form as. And so someone was using that to look at like cell migration in embryos. Really interesting paper. So that kind of model is kind of interesting in light of the type of typical developmental biology models where we're doing things like looking at cell physics, we're looking at cell to cell interactions, having
Yeah.
in considering the
Yeah.
autonomy of specific cells or specific tissues. So
Yeah.
I just think that the sort of the and this is more maybe a diva worm conversation, but how those different models kind of interact with these type of modeling exercises where we try to approximate what we think life is, I guess, what's important.
Right. And then to throw on the important, kind of leaven contribution to this is how is the bioelectric field changing, if at all. I mean, you can certainly imagine times where you've got flow, you got physical flow, but the field properties aren't necessarily changing.
Yeah.
Or are, like again, like another he's brought electricity back into as another level in which there's both, well, there's some sort of control,
right?
But again, that and then the interesting thing being that, of course, again, that control is, of course, collective.
Yeah. So the other thing to mention about this is there are a lot of interesting ties between the cellular automata work and then complexity theory, which I think one of the papers in the was mentioned was sort of out of Santa Fe Institute. So they've explored these kind of ideas quite a bit, especially with respect to emergence, and sort of how you have different types of emergence, strong emergence, weak emergence. How one of the things about emergence is that you can't really reverse engineer emergence, and how that kind of how that could be a model of life. So you have any model of life really, if you're thinking about like these different vertical levels of how life is organized. Any model of life is usually a higher level model, and so it entails emergence from, say, like a genotype to a phenotype, or from single organisms to like a community of organisms. And so you have this sort of vertical nature of life, which I don't know if our computational models can capture that necessarily. I mean, cellular automata seem to do that, but then having like the specificity that we have in life at these different levels of organization don't necessarily get captured by the cellular automata. It's just kind of a replication of it, of the process. Oh, we get these patterns. Great. It looks like life. Let's call it life. The game of life is like you see a glider moving. And you're like, oh, it looks like something swimming, and it's just something that's moving in pixel space. It's not necessarily, yeah. So,
I mean, it's the all models are wrong, but some are useful.
yeah.
I mean, yeah. I mean, again, it's interesting what you can explain with simple cell adjacency, cell interactions in a kind of flocking behavior in birds kind of way, right? That it can have all this flow and structure, if you will, of the group, but it's all off of very simple local interactions, and it doesn't, I don't think that it explains everything, but it's still, it's still remarkable when you see that multi-scale behavior.
All right. Yeah. All right. So, any other comments or questions before we move on? We've had this arc of talking about large language models and reasoning, and this was also posted in the Slack. I think this was also Morgan, where it's this diagram from a paper. It's figure 1 from a paper.
Yeah.
This is just kind of talking about large language models post training, and some of the things we do post training. So, you want to talk about this figure?
It is just an attempt to capture, like there's so much work going on,
Yeah.
right? So many different groups, and this is by this is one of the people that I follow on this is he's a French researcher. I forget where he works, but he's always run a group sharing papers, and this is the guy that we did a read through of we've done textbooks, we've he covers articles. I'm sure I probably posted the LinkedIn on this. Did I? Oh yeah, okay, here it is. Let me just quickly, yeah, and it includes this. 1 second. Second. So I'll put this in the chat. And here's okay. So that's just the archive and the associated GitHub. Again, it's the image. Do you mind blowing that up, or
Yeah,
my problem is finding my glasses.
Oh yeah, there we
go. Yeah, so and again, there's this plethora of. I mean, why are we doing all of this? Is because again, large language models are an interesting, was it fuzzy database of all our of training across all extant words and that can be found on the internet, and so all of these techniques are trying to when trained with such a simple sequential prediction model. Now there's all these attempts to get these sequences to well, I mean, to use one technique's name, to chain together better. to approximate something that is again our idea of what it is how we reason, and a lot of that is based on having so one thing is super important is that all of these depend on how we test them, right? So it's all down to what do we consider to be example problems that require reasoning. So we've now got a plethora of benchmarks that feature heavily with math problems and other kind of reasoning tests, and yeah, this is just a nice overview of where they are, and the different approaches. But I think I think it's one again, because I'll just do this until somebody shows me that I'm wrong. But bring up is it Emily Bender, and
Yes.
just we're doing all of these things because this is really not a good approach. and we train on all these benchmarks, but we don't look, we don't see we're not seeking out how the model is now insufficient when kind of this post training is done to optimize it for these reasoning benchmarks. So again, when large language models kind of started, she and Gary Marcus got together a bunch of linguists that it was really interesting to see the kinds of mistakes that large language models would make that linguists could find and could see, but you wouldn't capture from kind of natural language conversation, or you might gloss over them in the same way as like when a friend makes a mistake while speaking to you, and you just assume that they got confused about something, or they were thinking two thoughts, and like a mashup happened, or something like that.
Yeah.
And I think, and I haven't got the reference right now, but I saw a paper. Perhaps there's another. So that guy is Raymond. There's another woman, Cecilia. I also posted, I think, a link to her group. She meets online, and I think she's the one who posted paper that was like, there's some significant forgetting that's happening in these reasoning models, or these post training, certainly fine tuning, which again gets us back to kind of like the continual AI people.
Yeah.
In terms of that would be your expectation. You should expect the fine tuning to to use the old expression, there's no such thing as a free lunch.
Right.
Right. And so yeah. So if you're making a trade-off for improvements on reasoning benchmarks, like you should expect there to be an issue somewhere,
Yeah.
And yeah, I have no time whatsoever for AI doomerism or optimism, whatever, but there is not enough people thinking about these, there's not enough people doing kind of Emily Bender's kind of work.
Yeah.
And I think a big part of it is that this isn't just research, this is money. Right. So this is you can't swing a cat without hitting an AI startup founder in San Francisco. Sorry to all cats.
Yeah.
But yeah. Anyway.
Yeah. So yeah, this basically this inner circle is a large language model post training. Then they're talking about scale, reinforce, and tuning. Those I assume are sort of the post training alignment strategy. You have training, RL optimization, and decoding. So you're doing these kinds of different benchmarks, your chain of thought, tree of thoughts, consistency decoding for
yeah.
for scale and decoding.
I'd say those are the they call them those the algorithms.
Oh, the algorithms.
Yeah, and or the policies, or the
like
or
LHF and reinforcement learning, and then end-to-end prompt knowledge distillation for tuning, and then you have these models, which I guess are the ones where you have this post-training, or maybe they're most suited to this. I don't know what this outer ring is.
Well, those are what you end up with. So it's like it's trying to categorize. So again, it's just like it's crazy that there are I mean, in just this one example, you've got AlphaGo, Llama, Claude. Gemini is kind of from the same company as AlphaGo.
Yeah.
But DeepSeek, Quen, Mistral, so those are all separate companies' models.
Okay. Yeah.
That and again, it also reflects the fact that like even within a company, they've got multiple teams pursuing multiple avenues, right?
Yeah.
Because again, there's this $1 trillion pot at the end of the rainbow that they all think that they're in a race for.
Yeah.
And so no amount of funding is too crazy.
Yeah.
But yeah, so it's a nice it's a nice landscape picture.
Yeah.
Of that gives you a little organization. But you can also see some of these are represented in multiple avenues. Like I see DeepSeek on in the two outer areas.
Oh yeah, DeepSeek is actually in 2 of the categories. So.
Yeah. And it, which again, that was also the other interesting thing about the DeepSeek release on Spring Festival was that it was one of the only kind of big, it was one of the only super well funded groups, even though they were small, that told you about everything that they did. And released everything that they did. And so you got to see how, these are very complex, multiple training regimes and optimizations and things that, yeah. But again, all on ever increasing sets of benchmarks, and So I forget. I think it was Francois Chalet is obviously a good person to follow on this because he no longer works at Google, so he can say whatever he damn well pleases, barring some I guess it's NDA period.
Yeah.
Well, I don't know if you saw. There's a book that's coming out about an insider at Meta, and the book has been blocked by Zuckerberg. So it's supposed to be very not flattering picture of inside Facebook, and so Meta's blocking it based on forcing the author who used to work at Meta into private arbitration.
Oh.
Which is a technique that some of these companies anyway. Francois Chalet, I think was the person talking about, or maybe Carpathy, but some of these benchmarks are even starting to get, people are working their models to just get good, cat arena performance. And
Yeah.
And again, there's not enough broad testing of the models. And yeah, so
I like that expression, arena performance.
yeah. It's again, the arena was a good idea at the time. And it does give you. Again, it's important to know what are the important questions, and I think it's really interesting to go back to Tim Hansen's presentation on empathic AI. That we know. Yeah, I think it's interesting when you start looping a model back on itself, right? And which you could potentially say is a way for it to teach itself, but nobody actually does this in practice because it doesn't lead to better models,
Right.
or like that looping itself is still problematic, and yeah, so we have not achieved this strange loop.
Right.
to use Tim's talk.
Yeah. So this is this paper, What is a Number That a Large Language Model May Know It. So this is from the archive. This is new. This is basically where, I guess, where they're trying to introduce a concept of a number instead of just recalling numbers or things like that. So this is, let's read the abstract. Numbers are a basic part of how humans represent and describe the world around them. As a consequence, learning effective representations of numbers is critical for the success of large language models as they become more integrated into everyday decisions. So basically, it's like describing the category of numbers instead of kind of reciting numbers or giving a definition of numbers from a dictionary. So, it's like, well, a mathematical skill of describing all things in a set or all sets in a domain or whatever, and then like that definition will change. So it's like really how large language models deal with theory and theory building, which is, I guess, the practical consequence of that. So these are effective representations that you can then are expandable as you need to. However, these models face a challenge. Depending on context, the same sequence of digit tokens, for example, 911 or 911, can be treated as a number or as a string. So this, 911 might be like a phrase that people use for an emergency number, or 911 might be just three numbers in a numeric sequence, or it could be a string, which is actually part of like a sentence, a word in a sentence. So what kinds of representations arise from this duality? And what are its downstream implications? So the model has to be able to recognize the difference between the two, and it has to be able to do that. It has to be able to recognize context and these larger, these higher level sorts of categories. What kinds of representations arise from this duality? Using a similarity-based prompting technique from cognitive science, we show that large language models learn representational spaces that blend string-like and numeric representations. In particular, we show that elicited similarity judgments from these models over integer pairs can be captured by a combination of Levenshtein edit distance and numerical log linear distance, suggesting that an entangled representation. So Levenshtein edit distance is like looking at like two words. They could be, strings with different characters in it, and then looking at the difference in terms of character length. So if you're comparing two words like there and there, THERE and THEIR. The Levenshtein edit distance actually is, I think it's like 2 or 3, because you change some of the letters or characters in those two strings. And of course, there and there on those two spellings mean different things. So, so let's go back to the whiteboard. We can draw this out to show. So we might have there, and then there. And so your edit distance, I think, is 2, because you're changing these two positions, and you're changing the characters within this string. If you have, if you were to compare a string of 3 with a string of 4 characters, the edit distance would be 1, because you lose a character there. So there are these. That's Levenshtein distance, and it's used in computational linguistics quite a bit, and you can use it to understand sort of the edit distance between two words, but it doesn't necessarily give you the context. And it doesn't necessarily give you the context. Numerical log linear distance, of course, is where you get this actual distance in a different way. So this is an entangled representation where you get these two aspects of the words, and it allows you to build this sort of these meta categories in this context. In a series of experiments, we show how this entanglement is reflected in the latent embeddings, how it can be reduced but not entirely eliminated by context, and how it can propagate into a realistic decision scenario. These results shed light on a representational tension in transformer models that must learn what a number is from text input. So again, this is a quote from Warren McCullough, 1961. I think he was wearing a shirt at the time. That's good. And this is an inside joke for, never mind. So what is a number? That a man may know it, and a man, he may know a number. So this is like basically what is a number? So I can recognize a number if I see 1961. I know those are numbers. But then also, how do you know a number? What do you know? How do you know that 1961 is a date in history? Or that 1961 is like a measurement of weight? It could be 1,961 grams. There are different meanings of this combination of numbers. So yeah, that's the, and so they're using these representations to try to just make those distinctions, and
it reminded me a little bit of that PNAS paper with Brummelhard or no, the other one.
the other
That's
person
different.
or the other
Anyway.
paper? Okay.
Yeah. It's like a biblical passage, isn't it? Is what is a number?
Oh, I don't know.
I think, yeah.
Yeah.
Anyway, the McCullough paper is kind of interesting. Yeah, it's again, it's these funny things. I mean, just not necessarily what this paper is about, but just again, like the early problems that large language models had just doing arithmetic, and just getting at the point that, like, again, these are not artificially intelligent systems, but what was the artificially clever?
Okay.
I think was that Penrose's term? I forget. He had a different, it's fake,
Right.
It's like again, it's a large language model is not doing math.
Yeah.
It's not Right? It's not done, not learned its timetables or anything like that, right?
Yeah.
And so it's just like, if you ask, like again, like I it would be interesting to know behind the scenes what the various companies are doing,
Yeah.
so that it can do arithmetic right. Is it feeding it tables of like, if asked this, this is interesting. It just reminded me of the PNAS paper where they were asking people kind of questions about complex sentences, but they were asking people and LLMs, and this just focused on the LLMs, but I think it might have come from doing like I saw that one developmental psychologist. Anyway, I liked it.
Okay.
Yeah, sorry.
It's okay.
I'm trying to find the.
So let's So it's actually
they're talking about the that this came from some of like Stanislav Dehaan's work.
Oh, right.
So he'd done this kind of work with infants and stuff like that.
Oh, okay. All right.
That's one person. That's not the person I'm thinking of.
Okay.
Tenenbaum's who I'm thinking
right,
of.
Josh Tenenbaum.
Yeah. So I mean, I like people like Tenenbaum and Dehaan who actually work with kids.
Yeah. So let's go to this paper. This is the one that relative to it's relevant to that that figure we were looking at earlier. This is large language model post-training, a deep dive into reasoning large language models. This is from the archive. These are the authors on this paper. Large language models have transformed the natural language processing landscape and brought to light diverse applications. Pre-training on a vast web-scale data has laid the foundation for these models. Yet the research community is now interested in increasingly shifting focus towards post-training techniques to achieve further breakthroughs. So this is where now they're doing this post-training. That's where we got that zoo of models and zoo of techniques and all that. While pre-training provides a broad linguistic foundation, so there's the pre-training phase, and that's the foundation of the model, like what it can retrieve. Post-training methods enable large language models to refine their knowledge, improve reasoning, enhance factual accuracy, and align more effectively with user intents and ethical considerations. So fine-tuning, reinforcement learning, and test time scaling, those were the three categories. So if we go back to the figure, those are these three categories here: scale, reinforce, and tuning. And these have emerged as critical strategies for optimizing large language model performance, ensuring robustness, and improving adaptability across various real-world tasks. This survey provides a systematic exploration of post-training methodologies, analyzing their role in refining large language models beyond pre-training, addressing key challenges such as catastrophic forgetting, which we talked about, at least in terms of forgetting, reward hacking, and inference time trade-offs. We highlight emerging directions in model alignment, scalable adaptation, and inference time reasoning, and outline future research directions. So they have a link to their public repository, which is here. And that's this awesome large language model post-training repository at this in this GitHub account here. And so this is the README here. Large language model post-training a deep dive into reasoning large language models. They have the archive paper link, and then they have the corresponding authors here. This is the figure we just went over. And then the contents here, actually it's an interesting table because they give you, I think, a good mini review of some of this, these different papers. I guess these are links down to the bottom here. Yeah, so this is the table of contents to these different things in the review. Reward learning, policy optimization, exploration and generalization, and the different methods that they go over in this document. So, so like multi-agent reinforcement learning, you have emergent communication, coordination, social reinforcement learning, exploration and generalization is zero-shot reinforcement learning, generalization and reinforcement learning, and self-supervised reinforcement learning. And then, they have some of these other methods, policy optimization, offline reinforcement learning, imitation learning, hierarchical reinforcement learning. There's reward learning and some others. This is large language models for reasoning and decision making, causal reasoning, planning, and common sense reinforcement learning. So they also have this survey of papers where they kind of highlight different papers that are relevant here. And then they have these categories with papers associated with them. So this is a very useful resource, a large review here of these different. And then these are reinforcement learning and large language model fine-tuning repositories. So these are places where people have already implemented this. So you have things like Llama Gym, which simplifies fine-tuning large language model agents with online reinforcement learning. Instruct Llama implements pre-training, supervised fine-tuning, or SFT, and reinforcement learning from human feedback, RLHF, to train and fine-tune Llama 2. Train transformer language models with reinforcement learning, or TRL. That's a state-of-the-art library for post-training foundation models using methods like supervised fine-tuning, proximal policy optimization, GRPO, and direct performance optimization. This is a very nice resource here. Thank you, Morgan, for digging all that up, getting that out.
Yeah, they've got some really nice tables here, where they've really collated a lot of papers.
Yeah. Now there are no shortage of methods that they propose here for some of this stuff. Like there are a lot. It looks like people have done a lot of work in the area, at least of thinking about it and trying things out. But I don't know.
There's a lot of people working.
Yeah.
So if anything, I think it is somewhat, there's still a lot of well-worn paths that a lot of people are retreading the same material and kind of like variants of similar approaches.
Yeah.
But again, it's just yeah.
But of course, there's no accounting for which ones are. I mean, I guess you could say it depends on your application domain which one is best.
And again, so few of the, none of these are being developed to solve a particular problem.
Right.
In house. I mean, there's all the public benchmarks, and then I assume a bunch of in-house benchmarks or things. And maybe they've got some of their own in-house issues that they're trying to connect to these. But again, it's just all of these just well, deep sea, all of these come down to I mean, it was the Berkeley modal AI guy. It was just you're only as good as your benchmarks.
Yeah.
Right? Because that's the only way we can test it, and yeah. But I liked the beginning of this, just in terms of its, like, there remain, prone to critical shortcomings,
Mhm.
and this is their reasoning is, well, again, it's there's no reasoning. There's no real, or, well, certainly their reasoning is fundamentally distinct from human-like logical inference.
Yeah.
I guess, it's difficult to discuss them without the language assuming agency.
Yeah.
which again is is just a bit of a problem of using our language for basically meta language. But yeah, and again, I don't know who has this, but there should be a Bender Marcus benchmark that checks for is what is in fact being lost, or in some of these post-training approaches.
Yeah.
Or like subtle errors, subtle problems that will arise from post-training fine-tuning. I'll see if I can find that fine-tuning.
Yeah.
But
so I wonder if there's I wonder if there are problems introduced through fine-tuning that are, it's not included in the model. Like, if you think about natural intelligence, the reasoning kind of comes with the output. Maybe not always, but it's not. We don't fine-tune our output. I guess. Oh, maybe we sort of do in a social way, but it's kind of interesting comparison there.
There's definitely a little bit, but it's definitely being called catastrophic forgetting. So this is just I haven't checked in with the continual AI people, or I've probably missed their monthly seminar.
Oh, okay.
Okay. Well, their last meeting was focused on efficient fine-tuning techniques.
All right. Yeah. So why don't we move on? Looks like Sarrah's here. Well,
yeah. Hi.
Hi.
How's
How are
everybody?
you?
Good.
Yeah, I've been missing the past few weeks for a bit of a.
Oh yeah. No problem. Welcome back.
What's up? Yeah, thanks.
Yeah. I'm going to go to a series of papers and kind of close out the meeting with this category: intelligence and biological systems. Just a series of papers that one's a theory paper, one's kind of a review paper, and then the other is, I guess, another theory paper. I guess I'll start with this one here, which is the Nature Reviews Neuroscience paper. So this is, let me zoom in here a little bit. This is Daniel Barabasi, who is at Harvard, and
Northeastern?
he's the son of
Oh.
Barabasi from Network Science fame. So,
Oh, okay.
and he
I was
does,
gonna, like okay,
yeah,
because his dad's at Northeastern, right?
yes, and he's like the famous network science guy. This guy is a developmental biologist, computational developmental biologist. He works with Florian Engert, who's a C. elegans person, and then Andre Ferreira Castro, who's their author on this. So this is this paper is 3 systems of circuit formation, assembly, updating, and tuning. This is from Nature Reviews Neuroscience, which always has good reviews of things in neuroscience. So they've done some really interesting work on innate behaviors in zebrafish, and then also some things in C. elegans, which are interesting. Okay, so the abstract on this paper, understanding the relationship between genotype and neuronal circuit phenotype necessitates an integrated view of genetics, development, plasticity, and learning. So now we're no longer talking about large language models and how it does like forgetting and learning and things like that. And of course, we're thinking more about development. We're not explicitly talking about an emergent model, but we are talking about this sort of genotype to phenotype mapping. So we have genotype that informs the circuit phenotype or the connectome. And so this is a kind of a different view than the typical computational view, but challenging the prevailing notion that emphasizes learning and plasticity as primary drivers of circuit assembly. In this perspective, we delineate a tripartite framework to clarify the respective roles that learning and plasticity might have in this process. So these are the tripartite view. This is the tripartite view: assembly, updating, and tuning. Okay, so in the first part of this framework, which we term System 1, neural circuits are established purely through genetically driven algorithms, in which spike timing dependent plasticity serves no instructive role. So you have this, they're kind of drawing from the System 1, System 2, where you have like System 1, which is sort of basal behavior, System 2 being reasoning, which is actually, the way that you might think of kind of the way they're approaching large language model reasoning. You have the training phase, and then you have this post-training phase. So you have this System 1 and System 2 behavior. It's not exactly the same thing, but you get the point. So this is, in this case, they have 3 systems. So they have this 3-system framework. System 1, of course, is where you just have this genetically driven neural circuit. So we have genes that produce a circuit. So, if you go to, say, C. elegans or zebrafish, you can observe neural circuits that are basically the same across organisms. So they're driven by like environmental challenges or plasticity or anything else. It's just kind of like they're put into place in development, and they're basically the same. So that's System 1. Spike timing dependent plasticity, of course, is where you have learning, but you don't have that in the System 1. We propose that these circuits equip the animal with sufficient skill and knowledge to successfully engage the world. So this is where you have these kind of fixed behaviors, and they're invariant with respect to the environment. It's just kind of producing an output. Next, System 2 is governed by a rare but critical single-shot learning event. So this is where you have, this is maybe kind of like fear learning, where you have, if you've ever been scared like once, you usually retain that. If you have an aversion to something, like you don't like to go into a dark room, it could be because you were scared one time by being in a dark room and you have an aversion to it. You might have an aversion to certain foods because maybe you got food poisoning from that food once, so you never eat it again. And it works against like plasticity because you retain that memory in even in the face of conflicting evidence. So this is the System 1, which is where you have this sort of, System 2, where you have the single shot learning where you gain knowledge in a single shot, but then it maybe isn't adaptive. So this is which occur in response to survival situations and prompt rapid synaptic configuration. So this is where you learn something, you still don't have this sort of plasticity that will allow you to reorganize your synaptic connections due to any sort of new information. It's just encoded in a single shot. Such events serve as crucial updates to the existing hardwired knowledge base of an organism, but doesn't allow for this flexibility that we see in System 3, which is characterized by a perpetual state of synaptic recalibration involving continual plasticity for circuit stabilization and fine-tuning. So this is where you have this kind of continual learning or continual plasticity. You're always learning based on new information, and it's not single shot anymore. It's sort of just calibrating itself depending on what the environment is doing. And so by outlining the definitions and roles of these three core systems, our framework aims to resolve existing ambiguities related to and enrich our understanding of neural circuit formation. So assembly, updating, and tuning are these three steps, assembly being System 1, updating being System 2, and then tuning being System 3. So I don't know, they probably get into how System 2 and System 3 are related, because the single shot learning is what we often talk about or sometimes we talk about zero shot learning and machine learning and large language models. And it's sort of like this single shot learning where you're learning in one shot, and it's very efficient in the sense of being able to acquire information. But then this fine tuning is in biological systems a different step. And of course, the System 2 could be, in this case, can be maladaptive because you can acquire something in a single shot that maybe doesn't match the environment later. So you need to have the System 3 to sort of recalibrate that single shot learning. So you might learn something is bad, but then you don't necessarily give the nuance as to why it's bad. And so you respond to something that's bad just with a general behavior that's aversive, and then System 3 kind of brings a little bit more context to that. So you can learn different situational applications and why something is bad. It actually reminds me a lot of what Bratenberg vehicles are doing. So Bratenberg vehicles have a System 1 where they have this sort of wiring. And like in Bratenberg vehicles, you have different vehicles that have different wirings, and the wirings are fixed from vehicle to vehicle type. And then System 2 is where it might acquire a behavior, and again, that behavior is fixed for the phenotype. So you have this certain wiring, you have this behavior, it might be aversive, and you're kind of collapsing System 1 and System 2 here. But in my example, what I'm saying is that Bratenberg vehicles have the System 1 and System 2, they exhibit this sort of single shot learning. So, if you put it in a, say if it's has a native behavior that might make it attracted to light, and you put it in an environment with no light, it won't be attracted to anything. It'll just kind of move around according to Brownian motion. And then if you put it in an environment with light, it'll exhibit the System 2 behavior where it moves towards a target, like a light source. And then it still doesn't exhibit the System 3, of course, which is where you need fine-tuning. And then that's where you need to have sort of maybe a more complex circuitry or something that can be fine-tuned. So, this is, you can apply this to artificial systems as well, and it'd be quite interesting to see how this is applied to these different systems. Now, they take an interesting approach, even more interesting approach to this, in that they put it in the context of development. So, System 1 is sort of analogous to developmental maturation. So we think of like a fixed circuit, if it's fixed through genetics, as being fixed. And, actually that's not entirely true. There's this developmental maturation. So as this hardwired system gets put into place, and I think we talked about this last week, with Jesse, we had this conversation about plasticity and systems that are put into place, behavioral systems that are put into place at different stages of development. This system one is actually put into place at different stages of development. So you can have these sort of life history phases of this circuit being turned on. So there are all sorts of skills that kind of are acquired in newborns. So newborns can do certain things, that don't need to be learned. Sometimes they have aversions that are hardwired. So there are, different things. And they give an example of spider brains and newborn marine iguanas being able to detect and escape snakes. Cuckoo birds murdering their step siblings. So there can be quite complex behaviors that get put into place at different stages. And then, of course, you need to have, so they make the point here, innate and hardwired does not mean inflexible and stereotypical. So you can have these innate circuits that are, flexible in some ways, but they don't have the system one and system two aspect of acquisition. So they kind of give this, it sort of links together morphogenesis and learning, which is really interesting here. So this is a nice paper. It kind of makes these points very generally, and they're trying to build this theory here where they show these performance curves over trials, how people, in this case, are acquiring the skill of playing tennis. So actually, they have the point here in system two, you have these eureka moments, which are, I talked about fear learning, where you have this one-shot learning, but you also have these eureka moments where you start to acquire skill, like in tennis or in any kind of sport, and you kind of build that expertise, and then all of a sudden you have some sort of moment where the skill level jumps and reaches a plateau. And this often happens in training where you work with something for a while, and as you acquire the skill, you kind of improve, and then you hit this plateau where you've improved to a certain point. And it's a very quick consolidation of the memory. Sometimes, in discovery, we have this, I don't know if we talked about the aha moment, but that's in the literature where you have this, discovery. You kind of read things, you read all these papers, you finally put something together in a very quick eureka moment. So system two could be positive as well as negative, but it's this one-shot learning that has not as much nuance as system three, where you keep practicing, and in skill acquisition, you actually acquire skills through practice. You hit these plateaus where you acquire different skill levels, and then you keep practicing and you can make it to, higher and higher plateaus of performance. So this is kind of what they're getting at here. And then there's a biological basis for this, which they talk about here, with synapses and innate knowledge and all of that. Okay, so that's a nice paper. The next paper here I want to talk about is, so it's called A Theory of Intelligences. This is by Michael Hochberg. So this is A Theory of Intelligences, and the abstract reads, intelligence is a human construct to represent the ability to achieve goals. Given this wide berth, intelligence has been defined countless times, studied in a variety of ways, and represented using numerous measures. Understanding intelligence ultimately requires theory and quantification, both of which have been proved elusive. I developed a framework called the Theory of Intelligences, or TIS, that applies across all systems, from physics to biology, humans, and AI. So this is like kind of, we've talked about intelligence as being this poorly defined concept, especially for like artificial intelligence, because we kind of use analogies from human intelligence, and in the human case, intelligence is likewise pretty poorly defined. And so, but this actually goes across all these different domains. It's kind of like the Michael Levin cognition is everywhere approach, which goes back to what's his name, philosopher. What's his name? Well, anyways, so this kind of it's kind of like the Michael Levin intelligence is everywhere approach, but it also kind of gives you this kind of connection between natural and artificial intelligence. So TIS likens intelligence to a calculus, differentiating, correlating, and integrating information. So this is where you have this differentiable model of intelligence, but also this sort of mathematical model which you can easily apply to artificial intelligences. Intelligence operates at many levels and scales, and TIS distills these into a parsimonious macroscopic framework centered on solving, planning, and your optimization to accomplish goals. So this again is this sort of competency of goals aspect. Notably, intelligence can be expressed in informational units or in units relative to goal difficulty. So this is, of course, like bit-like kind of measure of intelligence. The latter defined as goal complexity relative to system ability, which can be individual complexity or benchmarked complexity. So you can have a benchmark or you can have like an individual assessment. I present general equations for intelligence and its components and a simple expression for the evolution of intelligence traits. The measures developed here could be the basis for further refinements to gauge different facets of intelligence for any stepwise transformation of information. I argue that proxies, such an environment, technology, and society, and collectives, so proxies being these environmental, technological, society, and collective aspects, are essential to a general theory of intelligence, the possible evolutionary transitions in intelligence, particularly in humans. So this is quite an ambitious theory, kind of thinking about information theory and how it can be applied to intelligence. Talking about going back to Claude Shannon and what he, his quote, information is the resolution of uncertainty. So basically the potential of information is as an unresolved order that can be perceived, filtered, deciphered, and transformed. Shannon had previously equated information with the term intelligence. Through his observation is but one essential part of intelligence, the other being goal attainment. So there's this kind of old view of Shannon, and he's thinking about information theory, and he, kind of understands that information is about resolving uncertainty. So if there's, uncertainty, you can't say that you have information. Information is only useful when it's certain. And so then you also, of course, have goal attainment and maybe some other concepts as well. This is just kind of what he's building towards in this theory. By associating these concepts, one arrives at a simple general description of intelligence. That is the resolution of uncertainty producing a result, be it reactive or an intentional goal. So if you have a system or a process that resolves uncertainty, it can be, that's intelligence. So if we have a genetic system that builds a circuit in a brain, that is, resolving uncertainty. If you have, like, say, a motor circuit, that motor circuit resolves uncertainty. You don't have to have a system of neurons that kind of have to come to this sort of behavior on its own. And so if you had that kind of system, say, if you had a bunch of neurons that kind of had connections between them, and you just had those generated in development, and the idea was that, every generation, every individual has to solve the problem of moving on its own, like moving around its environment. Well, that would result in, like, basically this random walk that you would do forever and ever, and only some organisms would figure out how to move maybe towards a goal or move in a coherent manner, how to coordinate their limbs and everything else. Having that kind of circuit hardwired into the genes and expressed in development in a very systematic way, resolves uncertainty. And so it provides the organism with intelligence. Now, it could be reactive or it could be towards an intentional goal. So you could have a reactive form of intelligence, which is building a circuit that maybe just does a random walk or a levee flight or something like that, and that would be fine. But then you also have intelligence that can sort of have an intentional goal, like move forward or move backward. And in C. elegans, for example, they have different parts of the movement circuit that do that. And so those are all sort of this, in the parlance of the last paper, this stage one behavior. So this is kind of consistent with that last paper. So the objective of this paper is to unpack this statement of his definition of intelligence and to use this to propose a series of increasingly complete frameworks in a theory of intelligence. So, yeah, I don't know if there are mathematical models we want to follow up with here. So basically, this is the key concepts figure 1. This is where you have this sort of this information gain over time, and then this planning versus solving graph. So let's see. All right, let's see if we can figure this out. Okay. So time versus, so first of all, planning versus solving. You have these different planning and solving. Okay. Solving is the ability to resolve uncertainty. Planning is the ability to trace a future sequence of manageable challenges towards goal resolution. The clines, which are these lines here across the graph, refer to the progressive intelligence milestones and abilities that deal with complexity. So you have these iso bars here in this graph, these solid lines that show kind of these, I guess, stable states or milestones that you make as you move forward. So you have 1, 2 trajectories, 1, 2, and 3. That's the dotted lines. Trajectory 1 is gains in intelligence, mostly due to solving. So you see it kind of parallels the y-axis, which is solve, and it crosses these different milestones. So you have these milestones that come across here. It reaches this 5th milestone sooner than trajectory 2, which is where it's dominated by planning. So solving is on the y-axis, planning is on the x-axis. So when your gains in intelligence are dominated by planning, you reach a lower milestone than if you do it by solving. And then 3 is this trajectory 3, which initially favors solving, but gradually favors planning, is the most efficient of the 3 examples. So you actually get to the 5th milestone sooner. And so what that suggests is that planning and solving are both part of intelligence. Then this section B, which is time versus information gain. This again has these 2. So there's a I, which is 1 here, is this monotonic decrease in path node changes, leading to an intermediate resolution that's efficiency. Number 2, which is this polynomial here, is complex trajectory and path node change with transient information loss, subsequent discovery of a more accurate path, and a consequential delay in resolution. And then 3, which is here, which is a straight line up but with a high level of information gain, is the sufficient path corresponding to a rapid resolution. So you see, he lays out these scenarios for his theory of intelligence and how it resolves uncertainty. Okay. So that's that paper. And, again, he lays out this mathematical framework. He kind of also lays out this idea of an intelligence niche. So this is these are representations borrowed from the ecological and evolutionary sciences, whereby the fundamental niche of a system or a species is the set of possible conditions for which the population can persist. So this actually goes beyond human intelligence in terms of natural intelligence and gives us this sort of phylogenetic view of intelligence. So we have this fundamental niche, which are traits, generalization, and flexibility. You have this proxy realized niche and this realized niche. The realized niche being a subset of the fundamental niche, which is context and environment. So we basically have, say, a fundamental niche would be like a neural circuit. And, that neural circuit can be flexible. And then the realized niche is where we have context and something that responds to the environment. So in the parlance of the last paper, the fundamental niche are these systems 1 and 2. The realized niche is system 3. And then proxy realized niche is where you have this augmentation. So it can be another form of a realized niche. And then you have this niche extension, which is selection, learning, and experience. It's also that sort of level 3. And then the proxy novel niche, which is where you extend and invert intelligence, and that's separate from this fundamental niche. So just thinking about this in terms of sort of different niches that an organism can occupy, specializations that they can exhibit. So basically you have this fundamental niche. It can be augmented, it can be refined through context, and then new niches emerge as a system of innovation. So like something like language or cognition. So if you have an organism that acquires high-level cognition or acquires a language, that's the proxy novel niche. Okay. So the third paper is this paper here. This is the natural history of intelligent systems towards understanding major transitions in cognitive evolution. So it draws from that sort of phylogenetic view of intelligence, and in this case, intelligent systems. One reason why this is interesting is that Adam Safron is an author on this. So it looks like Victoria Klimaj and Adam Safron are the authors. So that looks like this will be probably a pretty interesting paper. Actually, there are 3 papers in this series, but this is the one paper I want to highlight right now. I think this is like a preprint, and there are 2 other papers that are also preprints. So in the first set of explorations, meditations of 3, so this is paper 2 and paper 3, we examine major transitions in cognitive evolution and provide a framework for understanding different types of intelligence in naturally evolved systems. So they're looking at this sort of phylogenetic view. They want to understand different types of intelligence in these evolved systems. So it's not artificial intelligence, it's natural intelligence. And it forms, they have a common ancestry, of course, but they also have their own sort of adaptations and unique aspects. Drawing in synthetic perspectives from multiple theorists, we review several key taxonomies on cognitive sophistication, including Dennett's hierarchy of creatures. So Dennett was actually the original person who proposed sort of the cognition all the way down idea. Darwinian, Skinnerian, Popperian, and Gregorian. So this is Dennett's hierarchy of creatures. I'm not going to get into this concept, but this is where it comes from. Pearl's ladder of causation. Of course, Judea Pearl has worked on causation and has this sort of model of causation where you start with association, you move on to intervention, which can allow you to diagnose a cause, and then counterfactuals, which allow you to look at things that are contrasting and consider what-if questions. And then Tomasello's evolution of agency. Michael Tomasello proposed this evolution of agency as being goal-directed, intentional, rational, and socially normative. So these are kind of drawing from these different taxonomies of cognition, and as much as they're kind of, don't necessarily think of a phylogenetic view of intelligence as a ladder, because that would be incorrect. But they do have these hierarchies. And so, there are things that conform to different hierarchical levels of complexity, I guess you could put it. So this is kind of where they're going with this. We place particular emphasis on Tomasello's account, which traces the development of increasingly sophisticated forms of agency from early vertebrates to modern humans. So Tomasello's model is actually probably the most phylogenetic of the three taxonomies that we have here. So this is why they're kind of, looking at this sort of how agency kind of evolves. The paper also examines how unlimited associative learning, and this is something that actually comes from, this is a concept that's an earlier concept, not in this paper, but it was proposed as a method of sort of thinking about teleonomy and things like that. So unlimited associative learning may mark critical transitions in cognitive evolution. This review provides groundwork for 2 subsequent papers exploring social intelligence, human uniqueness, and artificial intelligence. We suggest that understanding these natural histories of intelligence may be crucial for developing artificial systems that can robustly engage in causal reasoning and social interaction. This theoretical synthesis offers insights into both the evolution of natural intelligence and potential pathways for developing artificial agents with sophisticated cognitive capabilities. So they're very much thinking about artificial intelligence here, but they're also taking this phylogenetic view and saying this is also important, and especially in terms of understanding natural intelligence. You can't just think about human analogs to intelligence. So this is the paper here, number 1. So this is the first paper, The Natural History of Intelligent Systems. This paper 2, this is the second paper in this series, the same authors, In Search of the Socio-Affective and Cognitive Origins of Humanity. What, if anything, is unique about human minds? So this actually kind of is the second set of these explorations, thinking about sort of comparing human cognitive uniqueness with non-human primates, focusing primarily on the theory of mind, analogical reasoning, and social learning capabilities. So this is something that is very much sort of Michael Tomasello oriented, and this kind of goes into some developmental and comparative psychology, how capabilities may emerge through the interplay of innate predispositions and social learning. So this is relevant to the thing we talked about in the first paper on sort of the systems 1, 2, and 3. And so they kind of get into these differences in primate cognition and how human cognition is unique in that sense. Paper 3 is this paper on Towards Artificial General Intelligence by Reverse Engineering the Human Heart Mind. And I don't know why they put heart mind. I guess it's because they're looking at... okay, so in the abstract reads, in this final set of explorations meditations, this is the third paper, we examine the requirements for developing artificial general intelligence, or AGI, through the lens of human cognitive architecture, with particular emphasis on the role of narrative selfhood and social cognition. Drawing on perspectives from cognitive science, philosophy of mind, and artificial intelligence research, we critically evaluate current claims about the capabilities of large language models, particularly regarding their purported achievements of theory of mind and self-awareness. We argue that genuinely human-like artificial intelligence may require more than sophisticated pattern recognition and language modeling. So this is relevant to what we were talking about before, where we build this model of sort of a training stage and then a post-training stage. And then we add in our reasoning in the post-training stage. So this is what we're talking about here. They argue that you need something more than that, potentially necessitating the development of coherent narrative self-models and rich causal understanding, special forms of ritually embodied and socially embedded development to achieve robust and reliable functionality. We conclude by proposing that the path to artificial general intelligence may require recapitulating aspects of human cognitive development, particularly regarding the construction of narrative identity and social moral reasoning capabilities. This analysis has implications for both technical development of AI systems and the ethical frameworks through which we evaluate artificial minds. Okay, so that's those papers. I know these last three papers, I suspect that they will be submitted to the special issue that we're trying to contribute to, and I think they're very much in line with that. But the third paper in particular is interesting in terms of this large language model reasoning quest. And so, yeah. So that's all I have for that. Sarrah asked a question in the chat. Also attended a talk this week which mentioned large concept models and how they might be a huge step towards AGI. So these are different than large concept models, not large language models. So yeah, we were kind of talking about that earlier, but yeah, I had not heard of these before. I haven't done much research on this yet, apart from the news about Meta's LCM models being released. Okay. Would people here be interested in exploring this? Yes. I could try to collect some papers and speak about them next meeting. Yeah, please do. We just got done talking about large language models and reasoning, kind of how they're doing this, and it's a zoo of ideas and benchmarks and tools. So yeah, I'd like to hear about concept models and how that's done.
Yeah, sure. I'll try that as well. Even I was like looking to read up about it, so it'll be a good way to do that as well.
Okay, yeah, great. Thank you. Do we have any thoughts about the papers that we talked about here?
Yeah, I mean, as usual, that's a lot of material.
Yeah.
So I mean, I always drop the links for us. I'm not sure what DLCA is. If you want to put it in the chat what that is. Just to say, yeah, hoping to meet with Adam next week. He said he's got a big meeting Wednesday, but would be freed up after that. Oh, yeah. Of course. The reverse engineering. Yeah, it's I'll get the links, Sarrah. We'll get all those.
Yeah. Oh, no idea.
Yeah. I was first finding them on ResearchGate, but they're actually all on SciArchive preprints. They're all on OSF.
Yeah.
Instead of searching on Adam Safron or OSF. But just to say that this is great to see, because I'd really like to know more details, like what he presented at the Foresight meeting. What is potentially like a year ago.
Yeah.
Is it that long? Anyway, but so the human heart mind is it's he's going for empathic AI.
Yeah. Oh, okay.
I believe. No, I got you now. Yeah. What projects exist, Bradley, that are perhaps using neural cellular automata?
I think people have largely just been exploring the algorithms and that. So, like, just kind of doing benchmarks and proof of concept. I'm not sure. I know that what we've been doing with the NCA is trying to grow an embryo network, which is something we've done in DevoWorm, where we take the cell centroids and we kind of look at their proximity or their signaling potential, and we build networks, and we kind of grow a growing network. So, like, as an embryo, as the cells divide in an embryo, you get these expanding networks, and the same thing holds true when you get like a connectome where cells are differentiating into neurons and connect to one another. So you get these growing networks in development, and you can use an NCA as part. So we have a repository on this where we're using it to kind of grow a network and show how, as the network grows, it changes its connectivity, it gets more dense, and all that.
So yeah, we started. We moved to daylight savings. Last
North America, last weekend.
Last weekend. So that's why you're maybe an hour off. Like, we should post in, what is it, UTC time, or
well, that wouldn't help
anyway.
Actually, but yeah,
it wouldn't help. This is the problem of finding a reference time frame.
Yeah.
Yeah, because I used to remember it used to be like 12 p.m. But then I don't know. I have a reminder that
we sprung forward.
Yeah.
So
Okay.
So in the States we moved 1 hour ahead.
Yeah. Okay. So what is like the just actual time with times? Okay, 7:30 IST. Oh, okay. So I've been. Oh, okay.
Thank
Okay,
you.
that helps me. The IST helps me.
Absolutely. and the Europeans will do it in like end of the month, I think. Anyway, so it's like for a couple weeks, the Europeans stay
don't have
in normal time, and then they'll switch.
Yeah. Okay. Yeah. Because I remember 8:30 and Okay, I'll change my reminders. So thanks.
Right.
Thanks, Vidhi.
Yeah, thank you. All right, so I guess that's it for today.
I wanted to mention one more thing.
Okay.
Which is that David Hough submitted a paper to an AI-generated paper to ICLR.
Oh yeah.
So anyway, I hadn't really seen this, but I think I saw some tweet or something about it, and it was just saying like he did this with permission from ICLR.
Yeah.
And I forget who was lauding it, but like, oh, this is a great step forward or something like that. But again, I
have to read it first.
Well, it's not just that, but like again, this is going through peer review is still just artificial cleverness,
right? Yeah.
And not but it would be interesting to look at it. And again, wanted to mention, somebody just sent me a link to this on Slack. Sorry, my Slack just quit. So, 1 second. Sorry. So neuropilot.chat is trying to make a chat agent that generates Brian 2, spiking neural network models.
Oh wow, okay.
And so it's just like I mention it just because I don't want to be the old man telling kids to get off my lawn.
Yeah.
About large language models, like they can do something, like this can still be useful. And I'm just curious if anybody's got a like who might be interested in trying this. Who's the Brian 2 guy? It's French.
Oh, I don't know.
Developer.
Yeah, but I
say. Actually, I want to say maybe like English speaking person who just happens to live in France. But,
maybe, yeah.
But anyway, not sure if anybody's interested in playing with that, but I thought that would be it might be nice, like Brain GPT, I think is the the Bradley Love, like are there some generating a paper doesn't actually seem like that much of a stretch for LLM. Right. Getting it to like again useful code generation or getting it to to really be a good assistant for literature searches or hypothesis generation would be kind of cool.
Yeah.
Anyway.
All right. Thanks.
Take care.
Next week. Take care. Bye.
Bye.
Bye. Thank you.
Bye. Thank you.
Bye.
Bye.